Hey, here's another screencast on the topic of right tail hypothesis tests. In the last screencast, I did a hypothesis test that involved fuel economy and gas mileage. And in that screencast, the hypothesis test looked something like this. The null hypothesis was that my fuel economy was greater than or equal to 12.1 miles per gallon. And my alternative hypothesis was my fuel economy was less than 12.1 miles per gallon. To test this hypothesis, we used some data, and we used a sample of measurements and calculated its p-value. So in this case, I think X bar was 10.7 miles per gallon. When we calculated the p-value, we did it based on the alternative hypothesis. And that is the chance that our fuel economy is the value of our sample or less. Right. And it's this that was operative, and this told us how to calculate the p-value. So imagine, here's the distribution. Here was the mu, and our X bar was down here, 10.7. And we calculated our p-value was this number right here, the area of that shaded region. And I forget what we calculated it to be, something like 0.288%. This is an example of what's called a left-tailed test, because we're working in the left tail of our distribution. Today, what I want to show you is an example of a right-tailed test, and you won't be surprised to see that the hypothesis test looks very similar, but these inequalities are going to be reversed. Hypothesis tests can be right-tailed, which I'll talk about today. It can be left-tailed, as I talked about last time, or they can be two-tailed. So I'll do an additional screencast that'll tell you about a two-tailed hypothesis test. But today, it's going to be a one-tailed, and it's going to be a right-tailed hypothesis test. Here's the scenario that we'll work within. A baker claims that their fresh baked bread height is, on average, more than 15 centimeters. Several of his customers ask for proof. To persuade his customers, the baker sets up a hypothesis test and bakes 10 loaves of bread, and their average height is 17 centimeters. So clearly higher than that, but is it a statistically significant difference? Well, let's find out. That's what a hypothesis test is for. The baker knows from baking hundreds of loaves of bread that loaf height has a standard deviation of 0.5 centimeters and that loaf height follows a normal distribution. Does his data support his claim? So let's set up a hypothesis test. So we'll have our null hypothesis and our alternative hypothesis. And our null hypothesis is that our average bread height is going to be 15 centimeters or higher. Oh, or lower. Sorry. Because that's what the customers believe. The baker believes otherwise. The baker believes that his bread heights are bigger than 15 centimeters. So this is the hypothesis test that we'll work with. So let's probably jump the gun by writing that down, but let's backfill a little bit. I'm going to use X to denote the height of a loaf of bread. And what does the baker know? The baker knows that the standard deviation of the height of the loaf of bread is 0.5 centimeters. And the baker also knows that the height of the loaf of bread is distributed normally. So with some mean, and we know the standard deviation is 0.5. So this means for us that because x is normal, we can conclude that the sample mean distribution is also normal with the same mean, and the standard deviation is going to be this, since the baker had a sample of size 10, so we know we need to divide by the square root of the sample size. This is great because then that tells us the sample mean has a nice bell-shaped distribution. That's a crappy drawing. And the mean there is at mu. What we're going to do is we're going to assume, give the customers the benefit of the doubt, that the mean is in fact 15 centimeters. So, let's also put that here. I'll do it in a different color so we know it's added later. So we're going to assume that the mean is 15 centimeters, and then we're going to look at the consequences of this. Right? In the last screencast, I told you this is kind of like a proof by contradiction. It's got that sort of feeling. So with mu assumed to be 15 centimeters, we have our sample mean here, x bar, is 17 centimeters. We want to calculate its p-value. So what's the probability that we got an average loaf height that was 17 centimeters or higher? Okay. And so this is where we see we're looking at the alternative hypothesis, and there's that inequality there. So what's the probability that our sample mean is greater than or equal to 17? Now remember, R and a lot of statistics tables, like the Z tables, they give us areas to the left of a cutoff. Here we're asked for areas to the right of a cutoff, so we're going to use the principle and probabilities of complementary areas or complementary events. So the probability that x is bigger than or equal to 17 is 1 minus the probability that x bar is less than or equal to 17. And with that, we can use R and do the calculation. So I'm going to move over to the next page and we'll do that. So our p-value is the probability that x bar is bigger than or equal to 17, which is 1 minus the probability x bar is less than or equal to 17, which is 1 minus, and so this is how we use R, p norm of 17. What's the probability that we were 17 given our normal distribution, right? That's what the norm means. Our normal distribution had mean 15 and standard deviation 0.5 over the square root of 10. Now, it's a little jarring, but when you plug this into R, and if you plug the whole thing into R is going to tell you get 1. So what that means is, what that means is that this probability here is approximately 0. For all intents and purposes, it's impossible. So how do we react to that? Well, we have calculated the p-value is approximately 0. So it's highly unlikely that the average loaf height of 15 of 17 centimeters actually is due to random chance, random variation. We conclude the assumption that mu equals 15 is incorrect. Rejecting the null hypothesis. Right, and that's how you'd end this. It might be a slightly better way to say this here. I might say, we conclude that this provides evidence to reject, the null hypothesis. And accept that mu is bigger than 15 centimeters. That seems like a more standard and conventional way of answering the question. And it's pretty similar to what I'd written before, but I might suggest the second way would be better for you. All right, that's the example. The one last thing that I would say is that here in the example, the baker claims to know that the standard deviation of loaf height is 0.5, right? He claims to know some information about the distribution of all loaf heights. If we were doing this problem and you didn't know that, but you had a sample standard deviation, you would proceed in exactly the same way, except instead of using a z distribution, the normal distribution, you would use a t distribution, a student t distribution, and you have 9 degrees of freedom. So that's the difference of having a small sample size or having a large sample size, or equivalently large lets you invoke the central limit theorem. But if it's you've got a sample from a normal distribution, you can assume that your distribution of the sample mean is normal. So I just wanted to make that point about what happens if you don't exactly know this. You have left, right, and two-tailed hypotheses tests too. You just use a different distribution. All right, that's it. See you next time.